It's really good to see all of you here this morning. I know it's a very early class, and you could conceivably probably do all the assignments without showing up, but it's much more engaging to talk to real people than just to a camera. So I appreciate you all being here. And let me know if you have questions as we go through all of this too. It's really helpful. If something gets lost, we can point it out along the way. I'll try to pause as we go. But today we're going to do my favorite topic in the whole universe, which is light. And light is what astronomy is really all about, because that's all we have when it comes to making sense of what's going on beyond our own atmosphere. Let's just recap what we did last week really quickly. Oh, I did want to point out one thing, actually. Somebody asked, and forgive me, I don't recall who that was, but somebody asked at the very end last time we were talking about calendars. Somebody said, why does the leap year get inserted in February? And I had no idea. I read into this a bit. And it turns out that most peoples before the Romans were marking the start of the year from the vernal equinox, which is in springtime. And so March being the first month of spring, they decided to tack on those extra days to February, which is kind of interesting. But last week in general, we talked about time and seasons. We said that seasons were something of, and climate to some extent, is something the result of this imperfect motion of the Earth, right? There's all of these different motions. It wobbles and tilts and gyrates, and these cycles all have different length. They have different time scales, right? So they can last hundreds of thousands of years, or it can just be a matter of a year, which is why we have seasons. So that brought us into looking at the Earth and Moon system and how the Moon affects life on Earth, and particularly the tidal systems. I perhaps mistakenly tried to cram in everything I could say about the Moon into last week's lecture. It turns out we have some space for it later on, which is great because we can get more into the compositional and exploration sides of the Moon. So we'll get more into that down the road. But like I said, today we're going to talk about light, which is, it's so vital and it's so poorly understood. And quite honestly, the deeper you get into the academic study of light, the more mathematical it will become, and the less mechanical sense it begins to make. So I'm going to do my best to walk you through how light might not be as spooky as people make it seem. There's perhaps ways we can think about it that are much more intuitive and much more, dare I say, mechanical. It's just that technology doesn't necessarily depend on us understanding those material aspects of nature so much, right? As long as we can parameterize something, that is, describe it in some equations that we can test with experiments, we can make incredible pieces of machinery that can take us to the stars. We can make radio transmitters, we can do all of this stuff. And it doesn't necessarily mean that we have to understand what the atoms are doing to one another. We just have to understand how they do it repeatedly in a descriptive fashion. So we're going to play with that. I want to walk you through very briefly the history of what people thought about light. So I think that's really important in understanding some cool ideas that maybe got lost and how they can play into our study of the stars in the future, because especially when we get into cosmology next semester, the interpretations that are being made about light at extraordinary different distances turn out to be often a little mystical and spooky. And I think that might come down to the fact that we don't totally understand what light is doing. And I've been having some really cool conversations with folks on my podcast lately, particularly a fellow at Caltech who's studying the conversations between atoms and the history of that idea. So I want to talk about that a little bit. And then the main technological advance, other than looking through a telescope and saying, okay, there's a cool star and it's this color and it's this brightness, is spectroscopy. And that's the idea of splitting light into its component wavelengths and analyzing the power density and the different elements that correspond to each one of those lights. So we're going to talk about that a little bit. I've been reading this really fantastic book. I believe it's called The Glass Universe, which is sort of the history of the development of spectroscopy, which turns out that it's this whole underground history because the men were away fighting in the wars in the early part of the 20th century. And so the women actually staffed all the observatories back then. And they unfortunately were written out of the history books to some extent, but there's this wild subsurface history of the development of this. And so I want to speak about that a little bit. And then finally, we'll talk about telescopes and how they work, and especially the modern telescopes, because you have all of these really wild looking arrays and radio telescopes and so forth. So I don't know if we're going to make it through all of this today. This is a lot to cover. The next lecture is supposed to essentially address a big picture version of the formation of our solar system, which we have time to get into the nitty-gritty stuff in subsequent lectures. So I think it's okay if we just introduce that topic next time and finish this up. But anyways, let's see how far we can get into it. So I'm going to assume that folks here know absolutely nothing about light, and that's totally fine. And I want to work towards an understanding of light as a wave, and really can ask you to consider what a wave is too. Because a wave is not a material object. I think that's the first thing to really consider. A wave is something that material objects do. It's actually a verb, right? It's to wave, right? Something waves. If you're in a stadium, you make waves. It's not like you have the people, and the people are waving, right, as they stand up and so forth. Or in a body of water, like shown, the water molecules are moving. They're actually being displaced, in one direction or the other. In the case of sound, when I'm talking right now, the air molecules are being compressed and relaxing. There's a periodic rarefication and compression of the air. So the air is moving. The wave is a phenomenon amongst the air. Okay, phenomenon, excuse me. Okay, so what did people in the first place think about light? It turns out that almost since the beginning, that people were thinking about light as some sort of a particle that was flying away from the source of the light. In fact, many of the early Greeks thought that when you were seeing, you were actually shooting particles out of your eyes in order to touch the things that you're looking at. And so I think the first person who wrote about this was Lucretius, who was a Roman in 55 BC, who actually had this atomistic idea that heat and light from the sun were being radiated and we were receiving them. The Indian Buddhists also had an interesting conception, an atomic conception of light, which involved actual beams of energy, which is this sort of nebulous mystical idea at the time. But I don't think that it's totally incorrect. I think we've talked about in this class how energy is best conceived of as similar to momentum. It's something moving, right? Energy always means something moving. It's not some spooky ghost that's flying around in the room. It means something is doing something. Something is doing something. Some material is in motion. And so the Buddhists are onto that. Then we flash forward, about 1,000 years, because there's this phase of the Dark Ages, particularly in Europe, but there wasn't a lot going on then, which is quite interesting. Or there wasn't a lot of record of what was going on, one or the other. The church controlled pretty much everything in Europe at the time, and they were not keen on rational explanations for phenomena. They saw this as a threat to their power structure. Whether it was or wasn't, they perceived it this way, and there wasn't much happening. So we flash forward like 1,000 years to Descartes, who we talked about when we were defining what a hypothesis was. And Descartes thought that light was some mechanical property of the body that was emitting the light. This was actually brand new. So this is about 1500-ish, mid-1500s. So this is, I mean, it's hard to even imagine 1,500 years passing before people really start to work on light again. But this happened. And he was actually somewhat at odds with the other thinkers of the day, like Kepler, who we talked about, Bacon, and others, who thought that light was actually different species of particles. So each one of these particles had its own flavor, and the light was a result of the particular species. But again, Descartes said, no, it's actually a property of the body that's emitting the light, which is close to how we see it today. Later on, people started thinking about this concept of how light travels. And actually, Newton comes into the picture again, too, who's one of the super demigods of physics, considered in some sense the birth of experimental physics and experimental science, or the father of these. But Newton incorrectly believed that light was little pieces of material that was flying around, much like the deep ancients. And he held this view to the very end. And to some extent, the only reason this didn't work out was because he couldn't explain, he believed that light couldn't be a wave, as other people were starting to speculate, because it didn't travel around corners, right? And he thought that if light was actually this thing that radiated outward, like shown here, that it should be able to go around corners. Now, what's fascinating is once we start talking about diffraction, especially when we get into spectroscopy, diffraction is this phenomenon by which light interferes with itself, and we'll talk about what that means. But it seems that actually, in a sense, that diffraction does actually show a situation where light is being reflected around corners. Now, it's not necessarily the bright part of the light that's being reflected around corners, although there's some of that too, but the dark part is also being reflected around it. And so you get these alternating fringes around corners. And we can do experiments with a very thin blade where we cast these bifringent shadows into the region actually behind the light. So Newton held to this idea, and there were other problems with this, what she called a corpuscular theory of light, these little corpuscles, these little blebs of material. In particular, he also believed that light should travel faster in a denser medium. And that didn't work out. Obviously, light travels the fastest in a vacuum. We know that at this point. And yeah, so let's see. So Hooke, we talked about Robert Hooke, who gave us the mechanical idea of springs and how deformation works, amongst other things. We talked about Robert Hooke, perhaps in some correspondences, even giving Newton the idea of the inverse square law for how gravity works. An interesting, well, let's get into that in a second, but it turns out that light also works with an inverse square law. And I think this is actually a really, really critical piece of information that has yet to be totally integrated in how we understand light and gravity, because they're so similar, actually, right? They're so similar in the way that they interact at distances. And so Hooke came along, and Hooke was really the first one to really champion this idea that light traveled as a wave, and that it spread just like water, as we saw on the last slide. And he called this his pulse theory, right? Like something is pulsing. Now, later on, a guy named Huygens, who is, we'll keep coming back to Huygens, he's a super boss of the era. He was able to put a mathematical theory to the wave nature of light and start to consider how waves would propagate inside of materials and how they would interfere with one another. And yeah, this wave theory began to be at serious odds with Newton's corpuscular idea, because it wasn't totally clear how a particle, a little bleb of something, could be waving. And actually, this is a complete nightmare up to the moment that we're in right now. And we'll talk about eventually the development of quantum mechanics and the photon and all of this. But needless to say, the wave theory began to take some precedence. And Thomas Young, around 1800, actually worked out the maths for how this interference happened. I believe this is one of his pictures. And so the basic idea is that if you have two sources of emanation, that the waves in, will overlap. There will be some impulse that will construct and some of it which will interfere. Now, all of this is very difficult to conceive of, but like I said, a wave is an activity, and almost all of these wave theorists believed in something which was later termed the luminiferous ether, which was sort of this material which filled the voids in between atoms. And, this was very, very popular all the way up until the early 20th century. And we can talk about why that lost popularity. But even general and special relativity, which Einstein developed, which are like the darling theories of modern physics. If you read Einstein's original writings, he thought of his concept of space-time, which is what you'll hear all the time as our pseudo-medium. He thought of space-time actually as an ether. He thought of it as a very particular kind of ether that would change its structure depending on what materials were nearby to it. And so I don't think that this ether concept is totally dead, although people today much prefer to refer to it as space-time, which is problematic because space-time is not simply a material. It has this time element, so it's actually a material that's in motion already. And so it's something of a kinematic ether. And this is quite interesting. So I think in this case, what they were imagining was that the ether was being compressed at these wave peaks, at these crests, as you see in the bottom left here. Sorry, my left, your right. And then it was being rarefied. And this was a workable theory for a while. It turned out that when they started, when some of the later scientists began to imagine it as an electromagnetic phenomenon, that they noticed that it wasn't so much this longitudinal compression, that light actually had this, what's called a transverse quality, where it actually emanated outward. The wave actually emanated outward, and I'll show you a picture of that in a second so you can start to make sense of it. So, here we go. So, what's a little bit unfortunate is that this discovery, which came about through the work of Michael Faraday and James Maxwell, that light had magnetic qualities, and that actually the magnetic component was at a right angle to the electric component, and that these were actually what were oscillating in space. So as a ray of light traveled, you had this oscillation in a sort of helical fashion about the center. Now, something really unfortunate happened actually at this point, and everyone looked back at the wave theory of light, and they said, okay, well, light isn't actually compressing in this longitudinal fashion like sound waves do. And so there must be nothing there. There must essentially, this ether cannot be, because these aren't compression waves. They're actually these interesting helical waves of oscillation about the center. And people started to turn away from the actual mechanical physical conception of light at that point, which I think was a grave mistake in some sense, because they moved on. And actually at this point, light began to be treated as a very mathematical phenomenon. And of course that works. Like I said, it works perfectly for technology, and we'll see how folks are able to develop radio signals and so on and so forth. I guess it's a good time to mention that when I say light in this course, I don't mean just the light that we see. I mean radio waves, X-rays, gamma rays, all of this electromagnetic radiation is light. So that's something to consider as well. in terms of the structure of whatever medium happens to be waving in this case, there hasn't really been a lot of work done on that. So maybe one of you will actually work on this in the future. But it seems that what's interesting about the kinematic ether of Einstein, the carrier of these waves of electromagnetic radiation, is that it does have a ray-like quality. Light does travel rectilinearly, that's to say it travels straight. And it does seem that that deformation of that medium is helical about some center, right? So I don't think that it's totally unreasonable, like when we talked about gravity before, to think about atoms as connected to one another. We can talk about that. And that it's connected by some sort of very rectilinear apparatus, which we don't totally understand yet. And that light is a deformation of that interconnection. So this is another piece of the puzzle too in the upper right-hand corner. This is the kind of the fundamental equation of light. You know, if you don't remember anything else, it's worth remembering that c is the speed of light, and it is held constant, at least in a vacuum. It does actually, the speed is a bit variable inside of media, and we can talk about why that is. But that the frequency f, if you multiply it by the wavelength, you are always getting the same value. So these things are unchanging, and that the rate of deformation of this kinematic ether, space-time, if you want to call it that, seems to be held constant in a vacuum, right? There's some maximum limit by which this medium can be deformed to produce these waves within it. And this is such that however fast you deform them, the frequency is proportional to how spaced apart those waves are, which is the wavelength, this lambda character. So something really interesting happened as folks were developing this electromagnetic conception of light, which Faraday actually set up in the first place. He discovered that you could actually polarize a beam of light depending on how you applied magnetic fields to it. That is to say that you could align those rays with regard to their rotation in a particular fashion. And this gentleman named Hertz came along, and we know Hertz because we use Hertz as the unit of frequency at this point, which really just means per second. But Hertz came along and did this really fantastic experiment where he was able to, I think I have a picture of this actually. He was able to demonstrate that by charging up this coil structure and creating a spark, at the bottom, you see here, there's this spark gap. It's able to create a spark at a particular frequency, a really fast frequency. I think it was in the megahertz, similar to what we use today for like TV transmission. He created this spark of ionized air, which is essentially what a spark is, in this gap. And then he had a coil, a single loop coil on the other side of the room, which is shown at the top here, with a similar spark gap. And what he was able to do was actually induce a spark in that coil at the other side of the room, simply by charging this oscillator at the bottom. And so this is the first demonstration that electricity could be transmitted at a distance, and that the frequencies of those transmissions synced up to one another. And so this is what became known as radio waves, and they were able to quantify this effect to the extent that they could reproduce it depending on how they tuned these coil systems. And this is essentially what we use to do radio signals today.
Doesn't a Tesla coil work on the same properties?
It is similar, yeah. It is also a coil structure. So there's a whole, if you get into electrical engineering, there's a whole world of electrical engineering called LC circuits, and it essentially involves how you build these coils. We use coils. We use this essential concept in order to build transformers, right? because you can't have the entire weight of the power grid coming into your computer system. So, everything you have has a little transformer system that actually has a series of coils inside of it that are transmitting that voltage at a very short length so that they can step down the voltage so that it's appropriate for your system.
I think also the whole idea of wireless power was another one of Tesla's ideas.
Yeah.
He had an idea for something called the warning sheath.
Yeah.
It was like
This is his laboratory.
It was like this giant tower on top of it that would just transmit electricity, but I don't think that they ever got working.
I kind of regret that I didn't mention Tesla more. He's quite a wild card. I mean, there's so much controversy around Tesla. He had essentially been funded by Westinghouse, who you probably recognize if you've lived on the East Coast. His name still is taken up by some of the power providers out there. And he was very much at odds with Edison at the time. And Edison was a great showman, right? He would put on these elaborate demonstrations in public. He would go to the different fairs and demonstrate how powerful his systems were. But in fact, some of the earliest developments were actually done by Tesla. Now, Tesla was a very disagreeable and he was very hermetic and he didn't get along with people very well. And he didn't tolerate people who couldn't understand his ideas. And despite the fact that he actually was probably a lot more brilliant than Edison, we don't, there are some vestiges of Tesla's legacy. Obviously, Elon Musk has taken that up with his car brand. But like you said, Wardenclyffe, he was working on transmitting power. And actually, down on the coast, if you drive down the coast to California, right before you hit San Francisco, there's a little town called Bolinas. And there's actually a power station outside of town where using Tesla's technology, they built this incredible wireless system. These huge plates out in the ocean. I mean, just this enormous structure. And they were purportedly actually delivering wireless power to the town of Bolinas for some amount of time. I don't know how much. But at some point, something went very wrong for Tesla. And it's kind of one of those interesting borderline conspiracy theories about what happened with Tesla, because his laboratory on the East Coast burned down mysteriously. And this was right around the time that Westinghouse pulled his funding. And he never really recovered from that. And actually, the FBI seized all of these documents, pretty much all of his life's work at that time. His station in Bolinas was swept into the ocean, dismantled and taken apart. And there hasn't been much work on that since. I mean, there are some wireless charging stations that are becoming popular now. I don't know if any of you have these for your phone or something. But in terms of actually supplying wireless power to a larger grid system, it has not taken off. And so there's a deep history there that's worth digging into if you have the time. It's actually very difficult to figure out the history of that sort of thing. The winners write the history books, and Edison was the winner. So, all right, back to light. So this is something that's really worth pondering, beyond this class, especially if you go into physics or if you go into some sort of science. If you'll recall, this diagram looks a whole lot like our picture of how gravity falls off at a distance, right? So if you pretend for a second that this is the Earth, on the other hand, and over here, you have the strength of gravity at a distance, you can see that where you have 4 points of gravity close to Earth, you would have 16. No, this is 3. So you'd have 9 points, 3 squared, right? It falls off with a square of the distance. The same thing happens with light. And so if you want to build a telescope, you need to catch all of that light in reverse. So if you're looking to a distant star, you want to capture all 4 of those rays, in this case, you need to build this array which has that proportional squared area to it. So this is really something to think about. This also started to bring in the idea that there's this thing called a photon. And the photon is an interesting discovery by itself too. So we've been talking about light as a wave, right? And there's this character about the wave, which is strange that it travels in a straight line, which we call rectilinear propagation. And so making sense and bringing these two ideas of how something like a particle can wave at the same time has been this endless challenge. And eventually the concept of the photon was advanced. They came up with the photon because it was actually done by Max Planck, who was trying to make sense of black body radiation. And we'll talk about black body radiation in just a moment. But the idea was that bodies, as you heat them, that they basically give off a spectrum of different wavelengths. And what was very strange was that according to the simple relationship between power, energy output, and the frequency of waves, that the power of those waves should go to infinity when you get down into really small wavelengths. In other words, the really small wavelengths like X-rays and gamma rays and even ultraviolet light, they actually would be expected to go off to infinity. So you would have an unimaginable amount of energy in these small waves, but it didn't seem to be the case. Actually, the power fell off very rapidly for ultraviolet light and downward in these black bodies. And so to mathematically rescue the model, Planck came up with this idea of a packet of energy that was relegated. So each photon can only carry a little packet of energy. What did that mean? Like each photon had this small impulse available to it. I suppose it's worth mentioning too at this point that light actually has a push to it, which is quite interesting. And there have been different discussions about how to make use of that push, especially in terms of powering spaceships across interstellar space. You know, the idea of a light sail that's actually catching the light and moving it back. So, you know, there's some really, really interesting parallels here between light and gravity because they both obey the inverse square law, although oppositely, right? Gravity is a pull, light is a push. And so there's something interesting going on there that we can actually learn, I think, about the structure of that kinematic ether that we call space-time. And this has yet to be fully developed. But I think that there's some real groundbreaking work that's going to pop up in your lifetime about that structure. Because again, a wave is an activity, right? It's an activity that some sort of objects must be doing. Now, later Einstein picked up Max Planck's idea and developed this a little bit further because he did a bunch of work and actually won the Nobel Prize for his work on the photoelectric effect, which was essentially taking this idea that little packets of energy were transmitted by individual moments of these beams of light, these rays, and that could be converted into a also similarly quantized piece of energy, which we call the electron now. And so people actually, for many, many years, and honestly, to this day, most textbooks are referring to light as if it is just this little thing that is shot outward, right? It emanates from a source, let's say from an atom, and that's it. I think this is a little bit of a tragedy because all of the empirical data we have about light comes from detecting light at another atom. And so for some reason, this idea that light is a conversation between atoms has gotten swept under the table. It has been pointed out across the ages. And actually this year's Nobel Prize in Physics had very much to do with this. And so you've actually heard probably about this concept of entanglement, that if you have atoms at different points in space, that they almost instantaneously will recognize the state of the other atoms under certain conditions, right? Which again makes us think about how these atoms might actually be connected to one another, either indirectly or directly, depending on the environment. And there's this really fascinating gentleman who worked in the tech industry for many years. His name's Carver Mead. I had a chance to speak with him over the weekend. And he's a Caltech Emeritus professor now, and he's really hot on interpreting all of these new breakthroughs and entanglements in terms of the conversations between atoms, and really seeing light as an action, as a transaction between atoms, as opposed to this, these things that are being cast off into the void randomly. Atoms don't lose mass just by radiating light. Newton's corpuscular idea didn't work out. Right? Things don't just disintegrate by emitting light. And so this quote actually is from G.N. Lewis, who is a very famous chemist. If you guys have taken a little bit of chemistry, you've probably heard of like the Lewis pairing of electrons. Lewis actually came up with the idea of the covalent bond. And honestly, the chemists are some of the most rational of all the scientists. They really see everything in terms of material interactions. Chemistry has to do with the combining of different shapes, right? Of different structures that are actually physically interacting with one another. And they do a bit of math, and they appreciate math, and it's quite useful in terms of quantifying their experiments. But at the end of the day, the chemists are always trying to make sense of what the material objects are doing to one another, which I think is quite wonderful. And I'm just going to read this quote to you because I think it's quite fascinating. This is from 1926. I'm going to make the contrary assumption that an atom never emits light except to another atom. I propose to eliminate the idea of mere emission of light and substitute the idea of transmission, or a process of exchange of energy between two definite atoms. Both atoms must play coordinate and symmetrical parts in the process of exchange. And I think this is just way ahead of its time and largely forgotten. Carver's written this book, I think, back in the 90s, which really elaborates on this concept. I would highly recommend it to everybody if you're interested in this subject. Okay. So, again, this is the electromagnetic spectrum. This is light across all of the different wavelengths. And you can see that at the far end, these really long waves are what we call radio waves. And we'll have different telescopes to deal with those. And at the opposite end, you have these really high energy gamma rays and X-rays. And actually, the interesting thing about these really high energy waves is that they're said to penetrate. They're penetrating radiation, which is bad for you because it can get down into your inner parts and your DNA and mess with things, which is not good. Radio waves, on the other hand, are really poor penetrators. And this is actually can work to our advantage because you can actually skip radio waves off of different structures. You can reflect them off of certain parts of the atmosphere and bend around the curve of the Earth, which is a very practically useful technique for people who are working in radio communication. And so light covers all of this, and actually this tiny little place right there is the visible spectrum where we can all see. Now, to have this a bit out of order, but when we go and look at how the atmosphere actually absorbs radiation in a moment, we'll see that there's this fantastic coincidence, probably not a coincidence since we all evolved on this planet over eons, that the atmosphere is essentially opaque to most of this radiation, right? It doesn't make it through the atmosphere. Most light does not make it through the atmosphere. The light that does make it through the atmosphere largely fits into this visible spectrum, which is just a fantastic coincidence because it means that we can actually see optically out into the night sky. Otherwise, it would be black. And of course, there are some other bands which are available to us at the far end, and we'll talk about those too. Because there is some radio astronomy that we can do from Earth, although it's dicey, and this has plagued astronomers. Not just radio astronomy, but atmospheric interference has been a nightmare for astronomers since the beginning. Now, I want to just talk for a second about how light is actually generated from these atoms. It's worth thinking about in terms of the bigger picture of this conversation between atoms. So this is a schematic representation of an atom. You have some surface of the atom, which we call the electron shell. This is where these electrons they're called orbitals, because originally we thought that the electron went around the atom like this, doesn't work out that way, actually. It's much more reasonably thought of as actually a shell-like surface on the atom. And that shell changes shape, and changes shape really, really fast. I think we might have talked about this when we were talking about atomic clocks. But the atoms are basically doing this pulsing thing, which is called a quantum jump. So it'll go between these different shapes, actually. The atom's actually changing shape. It might be changing, like, if it's just a simple hydrogen, it might just be breathing like this. Or let's say it's a complex atom, maybe its orbitals are changing to these lobular structures, and it's really undulating, doing this magnificent thing. But as it does this, it emits light at the same proportional frequency. This is really fascinating. So the atoms appear to be, somehow, through some structural means which we haven't really divined yet, they seem to be actually pushing and pulling on one another at some great distance. There seems to be a great vast relay network of these atoms doing such. And as they change shape, they're putting these alternate pressures on one another, which we can think about as light and gravity. I think that's the most sane way of thinking about light and gravity at the moment. It's not totally clear how that works out structurally, but it must be something like that. So as you get different colors as the atom goes through different particular breathing motions, these quantum jumps. And we can really start to see these individual colors being separated when we put them in front of a prism. We'll talk about that with spectroscopy. So before we get to that, it's really important to understand two things. And they come down to the work of essentially one gentleman who doesn't get enough praise in science. His name was Kirchhoff, and Kirchhoff and another gentleman named Wien. But Kirchhoff studied black bodies, which is a kind of a strange name, but the idea is that solid objects and liquids, to some extent, when you heat them, they give off radiation across an entire spectrum. And what Wien came along and realized was that the temperature and the wavelength of that radiation, the peak wavelength, that is where the majority of the power of that light was occurring, could be related to the temperature of that body. This is extremely important for astronomy when we start talking about what the colors of the stars mean. And it also might tell us a bit about the structure of the stars too, and we'll get into that more later. Now, I think it's worth taking a moment to talk about Kirchhoff himself and really the four laws that Kirchhoff determined, because they're absolutely the bedrock upon which modern astronomy is able to make conclusions about what it sees out there. Yeah. I know this is a lot of information, but I think that it's really a fascinating story. You good? Okay. So Kirchhoff, this figure summarizes Kirchhoff's understanding, and it is essentially what we use today for most of astronomy. Kirchhoff recognized, I'll just read them to you. So his first law was that a hot solid, liquid, or dense gas emits radiation at all wavelengths. He called this a continuous spectrum of radiation. So this is probably most familiar to you in terms of a rainbow of colors, which you see if you pass this solid body's light through a prism, or even just through some mist, as in the case of the rainbow, you get the constituent breaking apart of these different wavelengths. And that actually has to do with the way that different wavelengths have different speeds inside of media. And so each one of those wavelengths takes a little bit longer, loses some forward momentum, and it travels slightly separately, and you can actually separate these different colors out. So that was the first thing that he recognized. The second thing that he recognized was that a hot gas in front of a cooler background emits a radiation at a discrete set of isolated wavelengths. So gases, when excited, actually give off individual bands of radiation, only one frequency at a time. Okay. Now, this is really fascinating, and I've talked to a lot of people. One of my good friends who was a professor at Ohio State in the radiology department, he worked a lot with MRI, and obviously medical imaging has a lot to do with understanding how light travels and how radio waves travel. But he's really trying to popularize the idea that there's a mechanical reason for this. Gases are individual atoms, like we saw on the previous screen. There was this sphere thing, right? It's like a hydrogen. Well, the gases, a single simple object can only vibrate in a very simple fashion. It basically can swell and close. It can swell differently, but it can basically only vibrate along one or two different axes. And so the light that we get out of it would make sense. It would be very discrete, individual frequencies that you would see, wavelengths. However, a solid body, like the one that I'm sitting on right now, has an almost uncountable number of ways that it can vibrate. It can deform in so many different shapes. I mean, you can imagine a million ways to bend this desk, right? And so the light that's being emitted as those atoms change shape is essentially infinite. The different frequencies, the way that it can vibrate is essentially infinite. I think that's a good way of thinking about the difference between solid body radiation and gas radiation. Liquids are weird. They fall somewhere in the middle, but they do seem to give off a continuous band for the most part. Now, this is actually made for quite a discussion. I'm going to save the details of this for our discussion about the sun, because for when I was a child anyways, like when I was coming up through school, the sun was treated as a big ball of burning gas. And you can see almost immediately the problem with treating the sun as a big ball of burning gas, because the sun actually looks like this over here, more or less, when you split it with the prism. You can go try it yourself. And we do actually see some lines across it as well, which I'll get to in a minute. Those have to do with the atmosphere of the sun. So there is a solid-like quality about the sun, which people have argued over for ages. And there's a really fascinating history of the debates about the composition of the sun and what it actually is. And it's still going on to this day very much. Today, most scientists consider the sun a plasma, which is quite an interesting concept because plasmas can either be gaseous, they can be liquid. It's sort of this, we don't really understand what's going on except this body is nebulous. It doesn't seem to have the same solid-like character, but it's still capable of this continuous emission. They refer to it as having delocalized electrons, which is to essentially say that it behaves as a metal, but it's liquid, which is strange, and so on and so forth. So this is very important. Now, the third part that he came across was that a cool gas in front of a hot solid or liquid removes the radiation from the background source at special wavelengths. What this means is that if you stick the gas, like the atmosphere of the sun, in front of the sun, it will actually absorb at those same wavelengths that it would emit at if it was, say, electrically excited inside of a discharge tube or something. So you actually get little black bands when you look at the spectrum of the sun. You'll see these tiny little lines. Those correspond to what's happening in the atmosphere of the sun. That individual atoms are absorbing it, right? Again, because they have limited degrees of freedom as gases. They're just individual molecules. They can only absorb at specific frequencies. And we can talk about how that teaches us about the composition of the sun, or about the composition of all the stars. And there was quite an arms race to determine the classification system for those stars. And hopefully we'll have time to talk about that. Okay, I probably should have put this earlier, sorry. But this is the atmospheric absorption. I guess it follows because just like we have an atmosphere on Earth, the sun has an atmosphere as well. And this is what I was talking about most recently. The Earth also its atmosphere absorbs broadly because we have a high molecular content. We don't have just simple gases in our atmosphere. We actually have all sorts of complex molecules, from ozone to methane to CO2. And the Earth's atmosphere absorbs quite broadly. There is a little window we can see through with our eyes, the optical window, and then there's another window of radio observation at the far end of the spectrum. And this is really Kirchhoff's third law in action. This is the gas. This is absorption by gases. So when we went ahead and began to design telescopes, especially in the modern sense, we had to make use of this understanding. And it was a real nightmare because the early astronomers, of course, the first thing they did was start building the biggest telescopes they possibly could. And this turned out to not be the best approach because it turns out that location matters just as much as how big your collecting window is. And so there was a number of wonderful telescopes that were built in terrible places and had to be disassembled and moved. And there's some interesting stories there. Hopefully we'll get into them. So questions about light before we get too much into telescopes? If you think of anything, come talk to me later. Did we not do the fourth law? Yes. The fourth law is I'm really glad you mentioned that. Thank you. The fourth law, which is also really, really important, is that if something absorbs at a particular frequency, it also emits at that same frequency. And so there's a lot of predictive power available there in terms of if something is being screamed out, then we can also say that on Earth, if we do that experiment and we excite that same element and we see that same frequency, then we're pretty certain that that's what we're seeing at a very far distance where it's being absorbed. So yeah, that's a really important one. All right, so your basic telescope. Basic telescope has three main pieces. The first is the aperture. This is the bucket that you're catching all of these rays in. And obviously, the bigger the bucket, the more rays you can catch. The next piece that you have is this lens, right? And without boring you to death on optics, the lens is focusing the light. So it's taking those rays and it's essentially redirecting them toward some central point. This is important because generally when we're looking really far away, there's not a lot of light. You go out at night, it's pretty much dark outside, despite the fact that there are stars in every direction and there's an unbelievable amount of stars. The thing is, they're just so far away that because of that inverse square law, those rays have been diluted sufficiently that it's very hard to see things that are far away. So take all of those rays that we can catch in this however big of an aperture that we can fashion, and we focus them down to a small point. The final piece that we need to do is actually be able to take that tiny little point where we focus all those rays and then blow it up again. This is the magnification step. And so if any of you have thought about getting into telescopes, which you definitely should, actually we have a few of them in the department. So if you guys would be interested, maybe we can have like a stargazing night one time. Let me know if that sounds like fun. And what you do is you actually swap out the eyepiece. So your magnification will change just by, you don't have to get a new telescope to magnify something bigger. You actually just swap the eyepiece out. So modern telescopes, I would say that the eyepiece actually turns into something like a detector. And this is basically just a really nice eyeball that's capable of integrating over time, which is nice because a lot of the things that these beautiful pictures that you see of say the Milky Way or of distant galaxies, those are time integrated photographs. And what they'll actually do is they'll track the same structure for many nights in a row in order to collect enough light to actually generate those images. And so the ability to set up detectors that aren't just eyeballs has become really important. But let's back this up just a little bit. How old is this idea? How long have people been using telescopes? It might surprise you, but it seems to have not been that long, actually. The first mention of anybody really using lenses, that is like ground glass, to do anything optically other than make a trinket that looks really cool and makes cool light was in the 1400s. There was a gentleman named Nicholas of Cusa who was starting to correct people's nearsightedness with concave lenses. And it's just quite remarkable that this didn't occur to people until, only about, 500 years ago or something like that. Nicholas of Cusa was, by the way, he didn't come up, but he also had this idea that the Earth and the planets and the sun were all essentially the same thing. He called them all stars. He thought of the Earth as a star as well, which was really ahead of his time. It's about 100 years before Copernicus. And I forgot to mention him, but he's quite a character. So it seems around 1500 that Bacon came up with this theoretical idea. He sketched this in his notebook, this idea of how you could combine lenses in order to actually see things that were far away. And nobody seems to have really tried it out for a few more decades. Leonardo da Vinci also made some sketches in the 1400s, I believe it was. 14 to 1500s, about how this could be applied to see things that were far away. However, the first real telescopes weren't constructed until the Netherlands in the 1600s. So this is really quite modern. And those were, of course, initially being employed by the military because they want to be able to see the bad guys far away. So the Dutch were the telescope makers, and actually Galileo got his first telescope from the Dutch. The first telescopes could only magnify things about 3 times bigger than they were in real life, and this only got you so far. Galileo tinkered with his telescopes, and he was able to achieve something like a 23x magnification in his lifetime, which is how he was able to observe some of the moons of Jupiter and the phases of Venus and all of these things that sealed the story on the Earth not being actually at the center of the universe. So a little bit later, coming back to Kepler and Huygens. So Kepler had the idea that you could combine multiple lenses and actually do a bit more work that way. Huygens put this into effect, building these enormous lenses. He had actually a lens that was 12 feet wide, which I believe he suspended from a tree. It didn't have like a big tube like we think of as telescopes. Maybe he had maybe he had some sort of frame for it. But it was at quite a distance from his secondary magnification lens that we talked about. And he was actually able for the first time to see that Saturn had a ring structure. And there was, this was, let's say, this was in 1659. So relatively recently was the first time that we actually had this conception of Saturn as having rings. Before that, it was thought to be, maybe it was 2 planets that were very close to each other. Maybe it was very dusty. People didn't know. They could see that it was blebbed outward in this interesting way. But he really, I don't have his pictures, but he actually had all the different phases and how the tilt of Saturn changed across time. That was quite interesting. Let's see. Okay. So I talked a little bit about how prisms are able to split the different colors of light. And this is actually a very practically useful technique for much of the modern spectroscopy in terms of determining the elements the stars are made out of. However, it's a real nightmare for looking through a lens, because when you look through a lens, the different colors are being split unevenly. And so what this caused in many of the early telescopes was something called chromatic aberration, which is that basically all of these stars would have these strange colored halos. I'm sure they're quite beautiful, but they're a real mess. And so this led to a couple of ideas. One was people actually starting to figure out how to correct the chromatic aberration. which they did in this rather elegant fashion by essentially putting two lenses side by side, one that was able to have the opposite effect of the first one. They also started toying with the idea of using mirrors to capture the light instead of lenses to focus the light. So they could use these concave mirrors. And what's interesting about mirrors instead of lenses is that mirrors always reflect back the light exactly as it was received. Whereas lenses, the light has to pass through the lens. And most of our telescopes today are actually these mirrored telescopes. They're called reflecting telescopes, not the lens telescopes that we started off with. I think the department, we have some of these lens telescopes too, so maybe we can try them out. And you can see there is chromatic aberration on the lens one. There's some nice things about the lens telescopes. They're called refracting telescopes. To some extent, they're a bit easier to use. The images seem to be a bit more stable. They're heavier, but all of these things actually turn out to be introducing noise too. So today, we basically have these two systems. And as you can see, the mirrored one that I've been talking about is here on your right-hand side. And you essentially catch all of that light at the back of the telescope, and you focus it up towards a little point in the middle, which is then redirected towards your eyepiece. And then you can swap out the eyepieces and magnify it however you choose. And these are basically the two main systems that we use to collect light to this day. There's some other advantages to mirrored telescopes as well. It's very difficult to polish something perfectly, a lens, right? You also on a lens have two sides of it. A mirror only has one side, so that's half the work. The mirrors tend to be very heavy. Glass actually tends to deform when it gets heavy, and so there's actually a physical weight limit to how big you can make these glass lenses. Mirrors also tend to deform too under their weight, but it's a little more manageable. And so when people first started building these telescopes, they were quite enormous. This is one of an early reflector. This was at Mount Wilson in California. This is 2.5 meters, but you can see the apparatus to support it is quite enormous. Unfortunately, there's not a person in this. Oh, there is. It's a guy up on top there. Quite enormous structures to support the mirror, which is down at the bottom there. And then, today this is a modern mirror. I think this one's from your textbook, which went into the European Southern Observatories, VLT. It's funny they name these telescopes so drably. VLT stands for Very Large Telescope. Yeah.
I was wondering, do glasses affect what you can see through a telescope?
Yeah. Well, so your glasses are actually like your glasses. I believe your glasses have something similar to this correction, where they actually are correcting for the aberration. I take my glasses off when I look through the telescope because you can actually adjust the focus at the points of at the eyepiece. So yeah, I actually have contacts in right now, which are basically the same thing. So you can do it with or without, but I tend to take them off. You want to get your eye really close to it so you block out the world outside. It's easy to do with your glasses off. Right. So, the quality of these mirrors is extremely important. This one's 8 meters. And the bigger they get, the bigger these housings need to be in order to support them, particularly in regions where there's seismic activity, and just the tiniest disturbances can warp these and really mess up your image quality. And so this has become an ever increasing challenge. And I think we'll show some pictures later, but there's different ways around that. Particularly breaking the mirror up into lots of little mirrors that you then essentially use computers to reassemble the mosaic into one later is one of the main methods now. There's a couple more pictures. These are both reflector telescopes. First one's at Mount Palomar, which I believe is down in San Diego. And you can see it's quite interesting. Like This one has a tube. This one doesn't have a tube. They both function either way. This one still has a massive supporting structure that's able to keep that mirror perfectly positioned without deforming. Yep. So this is the one that I was talking about. I don't know if you can see this very well, but there's these little hexagonal arrays in this little hexagonal mirrors, which get around some of the deformations due to gravity and seismicity. And you can actually reassemble all of these images together. But the reflecting panel is large, but it's actually composed of individual units. And people have actually taken this to the next level, and they've come up with this concept of adaptive optics, which is very similar to the array model. But the idea is that you use these tiny little actuators, little motors, to deform the mirror, to put pressures on it in different ways so that you can actually program, you can study how, say, the atmosphere is affecting the reflection, and you can actually program the mirrors to deform to compensate for that atmospheric interference, which is pretty cool. And they have these going, at this point, they can do many corrections per second. And this has come a long way since the 80s when it was introduced. This is a good one. So this is that VLT. We looked at its mirror earlier. This is down in Chile. It has this adaptive octave system. It looks like something out of Star Wars, right? Because this is an unimaginable quantity of motors and circuitry and feedback loops that go into stabilizing these images, because it's actually deforming and repositioning these mirror arrays as it goes. Yeah, very interesting. Sometimes they'll actually use liquid crystal displays to filter the light and correct for some of these also, which is quite fascinating, like you would have on a calculator. You can screen out some of the light which would be interfering due to the atmospheric composition. Pretty cool. So, you know, a little, like I said, there's these telescopes that we use today. They're a bit more complex. We actually have, in most cases, some sort of filter that's inserted. You can see this filter wheel. This is essentially screening for different wavelengths that we want to look at. And we're not using our eyeballs, we're using detectors, because that allows us to actually integrate more time. With your eye, you're basically just getting a snapshot. But if you can look at something for a long time with a detector and collect that information, you can actually see things that are quite dim. And we use CCDs now, which is what you have in your camera. These are the idea that you have individual sensors. You actually have millions of sensors on one of these little chips, and each sensor is capable of detecting individual photons. And so the CCD stands for charge coupled device. So you're actually using the photoelectric effect to transmit your light energy into electric energy. Okay, what do I want to say about this? We talked a little bit about how light travels at different speeds in different media. This is actually essential to spectroscopy, which is what I want to spend the last 10 minutes or so talking about, because spectroscopy is where we really start to understand the elements that compose the various bodies that we look at when we look very far away. And it has to do with the separation of wavelength. So we know that light travels something like 300,000 kilometers per second in a vacuum. And that when it actually goes into a medium like water, there's a slowing effect. It actually goes down to something like 225 kilometers per second. And that this is wavelength dependent. And glass also slows it very similarly to water. And so as it slows, you can imagine that instead of all of the momentum taking this beam out through the other side, some of it is actually, some of that momentum is lost. And it's lost differently because each one of those wavelengths has a different amount of energy to it. So some of them are slowed less, and they separate, they bend less, and so on and so forth. So this is the principle of the prism, which is integral to the spectrometer. And the development of the spectrometer was just a really fascinating story. Like I said, a lot of this work was done by women during the First World War at Harvard's observatory, which is just such a fantastic story. I don't really have time to go through it all right now, but a lot of the telescopes that were doing this spectroscopic work were built by amateur astronomers. There's this gentleman named Draper, who was a physician at NYU, and he actually built some of the very first telescopes that were able to and developed the photographic method in his spare time. He had something like an estate up north on the Hudson, and he would actually. There's this story in the book where on his wedding night, his wife and him worked together, and most people on their wedding night like party or something. These people went out after their wedding and they shopped for skylights, which was the only real source of glass, large volumes of glass that you could get in that day, because they wanted to melt them down and make lenses for their homemade telescopes. And many of their telescopes, he died quite unfortunately and very young. He got some sort of respiratory infection when he was hunting in the woods, and he developed something like pericarditis. Actually, his disease sounds a lot like the one that we've all been dealing with for the last couple of years. Anyways, when he died, his wife took over the administration of all of these telescopes, and she reached out to the people at Harvard and ended up actually forming this long collaboration with them in order to transfer a lot of these telescopes by rail car to Harvard, and they formed the basis for the Harvard Observatory. Some of those actually ended up, like I said, once people realized that having big telescopes wasn't the solution, they actually transferred a lot of these all the way down to Chile, which was something like, it's very high there and it's very dry. So you can actually see very far without dealing with the atmosphere as much. And so those telescopes were built by amateurs, though, which is quite fascinating, I mean, I have no idea how a man who's a physician had the money to build, 20-foot telescopes, but different times, I guess. So the basic principle is that you redirect, you have a telescope just like normal, but you redirect some of that light through the prism system like we looked at, and you're able to see actually these colors forming different discrete bands across it. And you can actually see the absorption bands from the gas like we talked about. You can see the continuous spectrum. You can see how it separates out. There might be a predominance of one color for a certain star and less for another. Another thing that they developed, which is quite interesting at this Harvard Astronomy group, which was entirely developed by women at the time, was the idea of standardizing the luminosity of stars. Because we talked a little bit about this. I know it's quite confusing, but how bright something was very much just a subjective call. And I'm blanking on the name of the gentleman who first came up with this idea. It was very early on, I think in Galileo's time, that there was different orders of brightness of stars, and he called these magnitudes, and it's very subjective. These people at the Harvard Observatory, using these amateur scopes, were able to basically, they were able to develop a system where you had two different eyepieces. You split the light, and one eyepiece would be fixated on the pole star, say Polaris, and the other one would bring into focus whatever star you were interested in quantifying its brightness, its luminosity. And by having them side by side, you could turn a dial that would open the aperture a little bit more. And based on how wide you dial in that aperture, you could come up with a number to stick, a precise magnitude to hang on each one of these stars, which is really quite ingenious. And so in this way, they were actually able to standardize the luminosity of the stars. And, following this, people began to start to classify these these stars. And actually, interesting aside, the people that were analyzing all this data, these women, they were actually called them computers, which is really quite interesting. This is sort of the foundational. You've heard of this, yes?
Yeah.
Yeah, it's quite funny. So you read these correspondences, and they're all referring to the computers, which are actually human beings. And of course, the women were doing all the analysis of this data. They actually thought that the women weren't suited to be in the actual observing room because it was too cold for them or something silly like this. And so they were doing all these calculations, and they actually formulated the several different classification structures based on the temperature and the luminosity. And we're going to talk about star classification later, so there's no point in wasting all our time talking about that right this second. But it wasn't obvious exactly how you should classify them. I mean, there's problems with just classifying something based on its color and size, right? Like if you went out into the world and you tried to classify, let's say, plants just based on their size and color, you would have a very misleading conception about the origination of those plants, right? Because maybe cherries and strawberries actually have a similar size and color, but they really have nothing to do with one another in terms of stuff. You have to go quite a ways back evolutionarily to understand how they're related to one another. So this was a huge point of contention, and actually several of these women had different classification structures, and they ended up basically being synthesized by a gentleman in Europe much later on, and we'll talk about that when we get to it. Diffraction. So we don't really use prisms today. Prisms, of course, are expensive. It's very difficult to polish them, and so we use diffraction gratings instead. Most of you, maybe some of you are aware of this, but actually, when you look at a peacock feather, the colors are not actually the colors that, like if you put these individual quills under a microscope, they're actually not colored. The color comes from the splitting of the wavelengths by the surface of the peacock feather. When you get really far down, you find that there's arrays which are, in some sense, commensurate with the wavelengths that they're interfering with. So you're blocking out by the size of these contours on the structure of these feathers. You're actually killing off certain light, and you're reflecting back only the light which you see. And so this is the concept of a diffraction grating, that you can actually use the surface to block out certain wavelengths and let through others, and you can split them up this way. And so we use diffraction gratings in most modern microscopes, and this is what we see. So, we talked a little bit about this with Kirchhoff's laws, but each one of these elements has a particular set of shapes, a particular set of bands which are associated with how its atoms change in their energetic cycles. And you can do these experiments. Actually, Kirchhoff collaborated with Bunsen of Bunsen burner fame and came up with this. They kind of worked together to come up with this system of being able to identify in the lab various different elements by the colors they gave off and by the absorption that their gases, the absorption bands that their gases revealed. And this is basically what we use today for everything in astronomy. Actually, everything optical. And there are some other more advanced techniques which I believe we'll have to start off with next time. But this is the classification system that you're left with today, which is quite interesting. Actually, the names of it, you see that the star classification system, O, B, A, F, G, K, M. It doesn't make a lot of sense when you first look at it. Like, why aren't they just A, B, C, D? Well, actually, the ladies came up with this limerick, which was something like, "Oh, be a good." Yes, nice, thank you. "Oh, be a fine girl and kiss me," which is really funny. And we have a whole section later on in the course to deal with the classification system. And it's evolved a bit since then, and we'll talk about that. I just want to leave you with the cover of this book. I really am enjoying it so far. I'm about halfway through it. I really highly recommend it. It's by David Sobel, and it tells the story of how all of this work was done in the early 20th century and really the beginning of modern astronomy. So let's leave it there. Thank you, guys.